In this video, we'll continue working through Newton's second law and learn how it applies to more advanced problems where now the forces are given at certain angles. In the first 3 to 4 minutes, you will learn a step-by-step instruction on how to approach any problem in this unit, and then we'll look over one practice problem to demonstrate you how this method applies to problem solving. So if you're confused about your problems in class, keep watching because in these short 10-11 minutes, things will become really clear. Let's start by examining the method. So as always, our first step will always be to draw a free body diagram. And when we draw this diagram, we ask ourselves, what forces are present, right? Gravity, for example, is always present, right? Is there tension, meaning maybe there is a rope involved? Is there a friction in this problem, etc.? What direction are these forces, right? So gravity, for example, is always down. Tension is pointed along wherever the rope is, etc. And finally, so the difference between the previous problems and these ones are that now we have forces at an angle. And if we have these forces at an angle, we'll always find their x and y components and redraw the diagram with just the components present. If this doesn't make sense yet, keep watching because I'll demonstrate this step in this next problem that is coming up. And finally, choose the coordinate system, but typically to the right, we mean positive, and up is positive, and left and down is negative. So the second step is applying Newton's second law in both horizontal and vertical direction. So we simply write out all our forces in the x direction, all our forces in the y direction, right? And then we either set it equal to ma, right, if there's acceleration, or 0 if there's no acceleration, right? Typically, one of them will be 0 and another one will be ma, depending on the problem, right? Or the other way. Or both of them could be 0, but very rarely the object will be accelerating both in the x and the y direction. Finally, once you have your two equations in the x and the y set up, typically if there is a friction, we'll plug in the formula for the friction, which is mu times n. You don't have to remember it. You can reference your equation sheet. Just remember that there is a formula for friction, and you'll plug in all the known values and just solve these two equations, right? So if you don't know how to approach some problem, right? If you're kind of confused, okay, where do I start? Just follow these steps and I promise it will bring you to the right answer, right? Now, let's see how this method applies on one of these problems that could appear on your test or on your exam. Now, in this example, we have a towing rope, right? Of basically somebody's towing a car, a 2,000 kilogram car, at a constant speed. So when I read constant speed, I essentially right away thinking that, okay, acceleration is 0, right? This is one of those keywords that you should be able to recognize right away in the problem. The rope is angled at 20 degrees relative to the horizontal. Okay, so we have a 20-degree angle. Given that the coefficient of friction between the car and the road is 0.25, determine the tension required to maintain this motion. So we're looking for tension. Of course, I will start by drawing a free body diagram. So physicists are very creative. So our car is just going to be represented by a box, basically just like everything else in physics. So what forces do we have present? Well, there is a rope and we have to calculate the tension. So of course there is tension. And that says that it's at 20 degrees to the horizontal. What are other forces? There's always gravity, guys, pointed down. So there's mg pointed down. And since it's at the surface of the road, right, there is the normal force that will be pointed up, right, at 90 degrees to the surface. So strictly going up. And since they give us the coefficient of friction, there's also the friction that will be pointed to the left. So now with this additional step, right, now as you see, the tension is going to be at an angle. So what we have to do is we have to break down this tension in the x and the y components. And we do it by essentially drawing a right triangle where the tension is the hypotenuse and the two sides will be tx, so that's the horizontal component, and ty, so that's the vertical component right here. So let's remember our SOHCAHTOA, right? Sine is the opposite side ty over the hypotenuse. So sine of 20 degrees is going to be equal to ty over t. If we multiply both sides by t, we'll have ty is equal to t times sine 20. Similar trick we can do with the adjacent side right here, tx, right? Cosine of 20 degrees will be equal to adjacent side, which we call Tx, over the hypotenuse, which is T. If we multiply both sides by T, we'll see that Tx is equal to T cosine 20 degrees. Now, it's not a necessary step, but I still like to redraw this diagram by just including the components. So let me just do that. So what I mean by that is that instead of this tension right here, right, I will include a line to the right because the x component right of tension is to the right, and the x component we said was T cosine of 20, and the y component is up, so I will include arrow up, which is T sine 20, as we said. Let me see what I'm given, and I will go over to the next step, which is writing down the F net is equal to ma in the x and the y direction. Now, why do I think it's better to just write the components? Because as we right now reading the sum of all forces in the x and in the y direction, it's kind of easier to see that these forces are right across from each other. So for example, my forces in the x direction, as you can see, are T cosine 20, right, minus force of friction. Remember that to the right we consider positive forces, so that one is positive, friction is to the left, so it's negative. And up and down, right, if we're looking at, we have T sine 20, normal force, and mg. So T sine 20 plus normal force, because both of them are up, minus mg, because that one is down. Now, there's a constant motion. Remember these keywords of constant speed, which means the acceleration is 0. So it's going to be 0 in both of these dimensions, right? It's going to be equal to 0. So this right here is essentially 85% of the problem. And these are the same steps. You'll always be setting up this equation in the x and the y direction, as well as drawing the free body diagram. Another very common thing that we do is plugging in for the force of friction. So force of friction is mu times n, right? And the normal force we will get from this equation right here. So we will essentially rearrange this normal force by adding mg on both sides, right? So now I'm going to put it to the right and subtracting T sine 20. So now by plugging it in here, I can rewrite this equation as T cosine 20 minus mu times, instead of n, I can write down my expression mg minus T sine 20 is equal to 0. Let me open the parentheses. Mu mg, and negative mu times negative T will be positive. So as you see, the rest of this problem now is just algebra. We just have to solve this equation for the tension. So what I'm going to do is I'm going to add mu mg on both sides. And if all of these letters are giving you a lot of stress, what you can do is you can plug in the numbers. So you can plug in for everything except T here and just solve it in terms of T, right? So that one might be easier. However, I do advise to get used to seeing the variables, because most of us physicists love our variables. So I will factor out T from here. So it'll be cosine of 20 plus mu sine 20 is equal to mu mg. And then I will divide both sides by this parenthesis right here, right? So I will just take this parenthesis and I will divide by it on both sides in order to rearrange for the tension. So all that is left is just plug in all of my numbers over here. So mu was 0.25, the mass was 2000 kilograms, G is 9.8, cosine 20 plus 0.25 times sine of 20. And once I plug this into a calculator, I have my final answer for tension, which is 4,779.6 newtons, right? Don't forget the units. And here we have the final answer. In the next video, we'll go over the most common example in physics that appears on all of the tests and all of the exams, the inclined plane example. So keep practicing and keep watching these videos on your way to an A. Thank you.